welcome back to some more structural engineering. Today we'll be looking at another cantilever beam, but this time with an angled force. So let's see what we're going to solve, and let's solve it. Okay, so this is the cantilever beam that we're going to solve. You can see here that it's 5 meters long. At A there is a fixed support, and at B there is an angled load of 25 kilonewtons. Now we've been given, you can see here, this as an indication of the angle. Now some of you might remember this is a special angle, but say you didn't, we're going to solve this together. So what I'm going to do is I'm first going to figure out what that angle is. So if I take that triangle, right, it's a 3, 4, 5 triangle, and I call this alpha, I know that tan alpha equals 3 over 4. And if you do inverse tan on your calculator, you'll find that alpha equals 36.86 degrees. Probably sounding familiar now. What I'm going to do now is I'm going to figure from that force of 25 kilonewtons with this known angle now of 36.86, what my components are in each direction. So I want to figure out what my x component is, and I also want to figure out what my y component is. So my y component is going to be 25 sine alpha, or sine 36.86, and that works out as 15 kilonewtons. And in terms of my x component, it's going to be 25 cos the angle, cos 36.86, which works out as 20 kilonewtons. And once I know all of that, I am just going to draw my free body diagram as my first stage. So I'm going to replace this force here now, that 25, with its components. It's going to make it easier for me to calculate. So I'm going to put here 15 kilonewtons going down, and I'm going to have 20 kilonewtons here. And in terms of my support, I'm just going to replace that with AX, AY, and MA. And now that we have our free body diagram, and we've divided that angled force into components, we can find the reactions pretty quickly. Now, as we've mentioned before, finding reactions in a fixed end beam is pretty simple because AX, AY, and MA are in different directions, therefore they don't depend on each other, and we can get one variable per equation that we write. So if I start off by writing the sum of forces in the x direction, with this being my positive direction, I get AX minus 20 equals 0, so AX works out as 20 kilonewtons. If I then move on to write sum of forces in the y direction, with this being my positive direction, I get AY minus 15 equals 0, and so AY equals 15 kilonewtons. And the last thing that I'm going to write is sum of moments. I'm going to do them around A equals 0, with this being my positive direction. So in that case, I've got MA, right? That is the reaction moment at the fixed end. I've also got that 15 kilonewtons giving a negative moment, so minus 15 times the distance, which is 5. And we can see here that 20, AX, and AY all pass through point A, therefore there's no distance and they don't contribute a moment. So that is all I have. And so MA works out as 15 times 5, and that gives me 75 kilonewton meters. And the last thing I want to do is just create that free body diagram. So I'm just going to replace AX, AY, and MA with their actual values. AX worked out as 20. It turned out as positive, which means that the direction that I assumed is correct. So 20 here. AY worked out as 15, so 15 here. And MA was 75. So just replace that with 75. And that's it. Now that I've got those reaction forces, I've drawn that free body diagram, we're ready to find the internal forces. Now, as we can see here, we've only got forces at that fixed end at point A and that angled force at point B. Nothing changes between A and B, so we'll only need one cut, meaning we'll solve this pretty fast. Let's do it. Okay, we're all ready to solve the internal forces. As you can see, under my beam, I've just lined up space for the axial force, for the shear force, and for the bending moment diagram. Now, as we said, there's only stuff happening at A and at B, so they're going to be my main points of interest for this. We're going to start off by drawing a cut, and as we mentioned before, we're going to cut somewhere between A and B. So after we cut our beam, we're going to start from this direction here. So this is where X is going to start from. We're going to have to put our reaction forces at point A, so 20, 15, and 75. And we've now exposed at this cut the internal forces. So we're going to have N, our axial force, S, our shear force, and our moment of M. All these are drawn in the directions that we've already agreed on as our sign convention. And now all I need to do is find what N, S, and M are in general terms for each point along this beam and draw them on my diagrams. Let's start off with N. So I do this by sum of forces in the x direction equals 0. And in this case, I've got N plus 20 equals 0. So N works out as minus 20 kilonewtons. Since we assumed that the axial force N is in tension, this means that my axial force is actually in compression. I can just draw it straight away. So I'm just going to draw here minus, very important to note that this is compression, and 20. If I move on to solve the sum of forces in y equals 0, this will give me my shear force. In this case, I have minus S plus 15, and there's nothing else contributing to the y direction, so that equals 0, and S equals 15 kilonewtons. And once again, I can just draw that straight on. There's only one cut here, so that makes it pretty easy. So there we go, plus 15. And the last thing that I'm going to do is sum of moments. I do this at the cut. And the reason I do this at the cut is because it'll eliminate the shear force I've just calculated. So if I've made a mistake in that shear force, I'm not going to be carrying it with me. So let's see what we've got at the cut. We've got our moment, okay, should probably add this a function of x, mx, and then I've got that moment that I have at support A, which is positive, so plus 75. And then I've got the reaction force of 15, contributing a negative moment, so minus 15 times x, and that's all that contributes to a moment, so that equals 0, and therefore mx equals 15x minus 75. And if I'm interested in drawing this, I now want to figure out what happens when x equals 0, so point A, and what happens when x equals 5 meters, so point B. I might also be interested in what happens in the middle, or what happens at a quarter way. Whatever I've been asked, or wherever there's something that I want to design, I can figure it out quite easily from this equation that I've just solved. So when x equals 0, I get minus 75 kilonewton meters. And that means that if I assumed that m is like that, it is in fact not in this direction, it goes like this. And that means that it's pulling on the top, so tension on the top, and pushing at the bottom, so compression at the bottom. And when I draw my moment, I always draw it on the tension side, and that means that that tension side is on the top. So I'm going to draw it up here. So this is going to be 75. When x equals 5, I get 15 times 5 minus 75, and you can quickly find out that that is 0, and that makes absolute sense, right? This is a free end, so it makes sense that it's 0 here. I can see from my equation, this equation here, that this is a linear line, so it's going to be a straight line from that 75 to 0, and it's going to look like this. And just a quick summary of my internal forces. I found out that my axial force was in compression. We can see here there's no change in the axial force, therefore it's constant along the whole cantilever. I saw that my shear force was 15. Once again, started at 15, no change along the cantilever. And then I saw that my moment was linear. It starts at 75, right, which is the moment reaction at the support, and ends at 0 at my free end. And that is how you solve a cantilever beam with an angled force. Note that because of the angled force, we did get an axial force along this beam. And that's it for today. Thank you for joining me. Hope you'll join me again for some more structural engineering. Bye for now.